Closing years of the 20th century, astronomers made an astounding discovery that the universe is accelerating in its expansion, driven by a mysterious dark energy. But in the spring of 2024, the DESI project released results that hinted of another revolutionary finding that could revise our view of dark energy and the fate of the entire universe. Today, I'm incredibly lucky to host Professor Mustafa Ishak, a leading DESI scientist who will be revealing new results which should tell us if that hint of a revolution is real or a mirage. So welcome, Mustafa. How are you doing?
I'm doing good, thank you. Thanks.
So before we get into the results, why don't we start with a standard model of cosmology? What does it say about dark energy and the fate of the universe?
Yes, the standard model of cosmology is based on knowledge that we have for the last 100 years. And it tells us, it tells us that the universe is expanding. It tells us that, which we understand very well. It tells us also in 1998, so it tells us that this expansion of the universe is accelerating. So the universe is accelerating faster and faster. So our knowledge tells us that if that's the case, and according to the knowledge we have for the last 25 years, the universe then, the fate of the universe was that it will be ever expanding and faster and faster and faster.
So, but there is an assumption that this dark energy is a constant, has a constant value over time. But if it's not a constant, what implication would that have for the fate of the universe? Could it accelerate even more? Could it recollapse? What would it mean if it's not a constant?
Yeah, as you said, thanks to what we found in earlier this year in DESI, we found that the dark energy is not a cosmological constant, and it is, in fact, what we found is that we can use the word like colloquium word, it's weakening today. In other words, it's weakening. And if it continues to weaken, so the matter in the universe, the gravitational attraction of matter will take over. And that changes everything. That changes everything. It changes, in fact, the possibilities of the fate of the universe. So now the possibility that the expansion of the universe will slow down and will slow down and also, in fact, recontract is back to the table. It's not the only one. The universe can still just continue to expand, but no acceleration. However, one of the possibilities now is that the universe could just stop expanding and recollapse.
Right. So in a moment, you're going to reveal what the new data says, and I can't wait. But just before we get to that, why don't we just hear a little bit about how DESI works? What does it stand for? How does it work? How is it better than other probes of dark energy that we've had before?
Sure. So DESI is an experiment that was designed, that was thought to go after the properties of dark energy that causes cosmic acceleration. So in that, the dark energy candidates, let's put it like that way. So the universe is expanding, the universe is accelerating, so there are several candidates that could be there. And then among those candidates, how to distinguish them is the properties of them. So this dark energy will have a density, this dark energy will have a pressure. The ratio of the density, the energy density over the pressure is called the equation of state. So from now on, we will refer to it the W property of dark energy. So DESI was designed to measure to very, very high precision this W. And it does it because it was designed, the engineering of it, the architecture of it, is that it has it can measure to high precision two things. two things. It can measure to high precision the positions of the galaxies or quasars or objects, and also their speed, the speed they are moving with. It can measure this to high precision. And actually, why DESI? Because DESI uses what is called the baryon acoustic oscillations. It means it is using something that happened at the very, very early times in the universe. It's a sphere that comes from when the universe decoupled, when the universe very early, like 400,000 years at the universe, which is like 13 point something billion years from now, it left an imprint in the sky, and that imprint is called the baryon acoustic oscillation. I'm trying to dilute this so everyone can understand. You tell me when it's too technical. I can explain more.
Basically, these are like sound waves in the early primordial universe.
Yes,
Is that right?
Yes, the universe was a plasma, and there was a competition between the photons and the baryons. So the gravity was trying to bring all these baryons together, collapse them, and the photon had pressure and was pushing back. So there's these oscillations. But from the time of the Big Bang all the way to this kind of Z redshift of 1090, which means like the universe was something around 400,000 years, there was not enough energy because of the expansion of the universe. So there was this kind of decoupling, and then the photons went free. The baryons went free. However, when the baryons went free, this last oscillations has a radius, some radius that we can calculate. And we can find it. How is that radius? So we know the initial radius, and then the universe is expanding. So when we measure it, we measure that radius, and we compare it to what it was initially, so we can find information on the expansion history of the universe. So if we look in the universe, the matter is not distributed randomly. The matter has some spherical shells that we know the standard radius, and then we measure that radius in the transverse direction, and we measure it in the longitudinal direction. One and the two of them, they give us the information on the expansion history, and then the longitudinal one gives us the delta Z, delta redshift, and gives us the speeds. So that's what DESI does the best, and that's how it finds to high precision both the position and the expansion history and the speeds of the receding speeds of galaxies.
Right. So before, I think it was spring of this year, you had like 1 year of data. So what do you have now? And why don't you tell us the big question, which is, have you confirmed this exciting finding that dark energy is changing over time, or has that gone away? That's the really big question.
So in two words, before that, let me explain the context. So we are still working with the 1 year of data. The new thing we are using now, and we did not use in April, it's like the speeds, the velocities, actually we call it the full shape measurement. So there is clustering of galaxies, and this clustering of galaxies we quantify that with the power spectrum. The power spectrum of galaxies, the power spectrum of matter. So
we should just say the power spectrum is like what we see when we look at the cosmic microwave background, the relationship between the different temperature fluctuations and their angular scale. Is that right?
Exactly, that is right. This one is the correlations between the galaxies at different positions. And that information tells us how galaxies and quasars and so forth, how they cluster, the rate at which they cluster. It happens that the rate of clustering of these objects, that rate is very closely related to the underlying theory of gravity. So what we have now it does add some information to the measurement of dark energy from April, which was, I think, if I have the opportunity a little bit later, I will say a few words about it. So that was a huge discovery, a huge finding about dark energy in April. That is not, it seems not to be a cosmological constant. So now we do find again that results, not with more data, with the same data, but we add to it this galaxy power spectrum, So we add to it this information. We call it the full shape of the power spectrum. So we add to it this information. So this again confirms the dark energy is dynamical. It confirmed that result. But additionally to that, it does something very important this time. And that's the big thing, is that it tells us that DESI data, DESI measurements are in agreement with the theory of gravity of Einstein. That's the big thing this time. And to be clear, this doesn't mean we exclude all the other theories of gravity. This means that it's very consistent with general relativity of Einstein. There is still room of some uncertainty and some room for other theories. It's not all excluded. However, the big plus this time is that, and this appears in the two in the papers we will release tomorrow, the general paper from DESI, but also there is a paper dedicated to testing gravity at cosmological scales. There is details there, and some details there is that they show that not only we are consistent with the theory of Einstein, but also the result of cosmic acceleration and dark energy being dynamical stands.
Right.
This
so let's
is
just
big.
give a little bit of context to that challenging Einstein. So just for people watching, some people have suggested that maybe instead of dark energy or also dark matter, you could modify Einstein's equation slightly, and you'll have a new theory very similar to Einstein, but maybe not quite the same. So what you're saying is those theories don't look very good at the moment, but if we keep Einstein's theory, but we keep the cosmological constant, well, not a constant, but varying over time, then we get a good fit to the data. Is that right? If I understood that right?
That is correct. That is correct. In other words, we had one thing in April, which is I think working on dark energy and cosmic acceleration for 25 years, that result was a kind of a dream coming true, in the sense that some of us did not expect that to happen in our lifetimes. It could have happened in 10 years, 20, 100 years, 200 years. It was really an incredible blessing that it happened. We're still recovering from that. However, yeah.
So
Please go ahead. Yeah.
That in April, if I recall correctly, well, I should say scientists have these things called confidence levels, sort of 2 sigma, 3 sigma, 4 sigma, and like in particle physics, so discovery is 5 sigma. I think in cosmology, I've heard some people say it's more like 3 or 4. And if I remember rightly, the results were like high 2s, like on the borderline of this is interesting. Have you changed that sigma value? Where do you stand now?
The sigma values, those sigma values will change next year with the 3-year data of DESI. What we have now, if we have a repeat, those values came again the same. So we have a repeat of those values. In other words, we still have the 2.6, 3.5, and 3.9 data. And also, the important thing is that, so that answers your question. The new thing is that not only that stands, but also we are able to put into the model the possibility that the theory of Einstein is changing, is not, there is deviations from the theory of gravity, but we don't see it in this release. So we do repeat those numbers. We still get them more or less with very tiny departure from them, but also at the same time, we find that the theory of gravity of Einstein stands, which is amazing because, or again, which is new to me. That there where is the new thing. In other words, in April we said this. We said, oh, there is a deviations from a cosmological constant. That's great. We were stuck with it for 25 years. Now we are kind of unstuck. We don't know what it is yet, but we know it's not. It looks not to be a cosmological constant. But what is it? A lot of us thought it might be the symptom, the sign of a modification to gravity. But now this result is saying actually, not only it's not a cosmological constant, it might also not be a modified gravity. So then the big point, yes.
Yeah, there are these modified gravity theories, but there's also some quantum gravity theories. And one that springs to mind, I'm not sure if you're familiar with it, but there's a theory called causal set theory. And my understanding is they predicted that the cosmological constant would change over time, that it wouldn't be a constant. Is there? Have you looked into that at all, or have you only looked?
What is the name of the theory again? It cut a little bit.
It's called causal set theory.
Okay, causal set theory. Yeah, I'm not familiar with that particular theory. However, what we did not go after it in particular. However, what we did, we took an approach. We took the following approach: is that we said, let parameterize, let represent any deviations from general relativity by two parameters. A parameter that measures how the matter, the galaxies, and so forth, they cluster in the universe. And the other one is sigma parameter, is for the lensing, gravitational lensing. So DESI is a chief experiment to measure mu, to measure this clustering.
Just clarify, gravitational lensing is when the large mass of galaxies curves the light, and we get these weird distortions, right?
Yes, that is correct. That is the light, the motion of light is deflected by gravitational object, and theories of gravity can deviate from general relativity in two ways, at least. In two ways. One way, it tells us how the matter moves in the universe, how massive objects that have mass, like galaxies and so forth. And it also tells us how the light moves in the universe. So our results with DESI is one of the best, if not the best experiment to measure this, how matter moves in the universe, and goes after what we call the parameter mu naught. And so it's in other ways some way to have a generic way to see whether we deviate from general relativity. And then once we find that we deviate, now we say, okay, if we are deviating from general relativity, let's see what this parameter mu naught and sigma naught tell us, and then what are the modified gravity models that correspond to that. Like, for example, there is this Hordensky models, there is this massive gravity, there is this entropy-based model. So there are several models, and there's the model that you mentioned. So all these models, we cannot go after them individually, but we can go after them in a generic way, let's say parameterization, and look for deviations. And we haven't seen any.
Wow, okay.
It's not a perfect way, but it's a nice way to do it.
So let's look to the future, because presumably we want to get that sigma level up higher. Will that happen when you release the 3-year data? And if so, when are you going to release the 3-year data?
Okay, so the Yeah, the data that we are working as we speak. It has been a crazy journey, a nice journey of work, but very busy. So at the same time, we are wrapping up and getting these results to come out, but we are also having our hands into the year 3 data to get to release the data. So the magic month will be March 2025 if everything goes according to plans. So we will release. Then we will have these higher sigmas. How high they will be, we don't know yet, but they will be higher.
Right. And so just for a bit of fun, if you had to bet when the March data comes out, is this changing cosmological constant going to be still with us, or is it going to disappear and be a bit of noise
All
and
right.
go down? If it gave you 50-50 odds, what would you put your money on?
Look, I am waking up, as you know, here in Dallas. The night was short. You know it very well. And I actually, let me put it this way. I really like it that you ask this question. And I tell you exactly why. My opinion is that my bet is that it will stand. And of course, what is important is why do I think that?
Yeah.
I might be wrong. We have to be prudent. But this is what I find to be important in cosmology. It's the trends. It's not one given number like 3.9 sigma, which is significant, but the trends of the data, trends are more important. So we have 3 probes. We have CMB, cosmic microwave background radiation. We have the supernovae, and we have DESI, the BAO measurements. So these 3 data sets, they all tell us the same story. So if we take 2 at a time, let's say I wake up one morning and I say, I don't like supernovae, and I will use just CMB and DESI. They do give us a 2.6 sigma deviations from a cosmological constant. So trends are important. And I take supernovae and CMB, and they tell me the same story. So if I take any two, if I take supernovae and DESI, just DESI, and then I add to it any one or 2 sets of actually supernovae, one at a time, with union or with DES year 3, year 5 supernovae. They tell me the same story. So to me, trends are important. And so we're up to something really exciting. Again, some of us, when we saw this in December, the night of December 12th, 2023, for the first time when I saw that on my Jupyter notebook doing plotting stuff, I knew something, we were up to something special, something new. And I think, so my opinion is, I would expect this to stand. If it turns out that all these different probes have different systematics, that they all contribute in the same way to have this 4th quadrant of dark energy, it seems to me unlikely, but still possible. We will see.
Right. So
I'm very hopeful.
Come March, you'll come back with the 3-year data, and then we're going to know with a lot more confidence if we're going to be revolutionizing cosmology with a changing value for dark energy or not. So will you come back in March and share us your results?
Yes, it will be my pleasure. And who knows how the excitement will be at the time.
Right. Well, we look forward to it. In the meantime, thank you so much, Mustafa. It's been an amazing journey listening to what's cutting edge in cosmology. So thank you so much.
My pleasure. Thank you.